So, getting on to our review of electromagnetism. So, we're going to be going back over electrostatics. So remember, electrostatics involves charged particles which create an electric field and influence one another due to their charges. The reason that we call these electrostatics is because the charges are staying stationary, electric, stationary, electrostatics. However, when we get into magnetism, the charges are going to be moving, and because the charges are moving, they're generating a magnetic field. So, when we're talking about electrostatics, we're talking about the force generated by the particles due to their charge. So, to calculate the force on two charges due to their electric field, we need to use Coulomb's law, which is in your formula sheet. It tells us that the force between the two charges is going to be equal to Coulomb's constant, and that number is in your formula sheet as well, multiplied by the two charges themselves in coulombs and divided by the distance between them. So what this tells us is that a greater force is going to be exerted if the charge on the two particles is greater, and the greater force is going to be exerted if the particles themselves are closer to one another. Again, similarly to with Newton's laws and gravity, the force acting on the two objects is going to be equal. Because remember, applying Newton's laws, every action has an equal and opposite reaction. So even if the two particles themselves have different charges, the force exerted on both of them is going to be the same. Okay. The direction of the electrical force is going to depend on the charge. So remember, like charges repel, two positives are going to move away from one another, two negatives are going to move away from one another, but then the opposite charges attract. So, electric field strength is given or measures the intensity of the force experienced by a charged particle in an electric field. And this is going to be given to us by the equation electric field strength is equal to force divided by charge, or in other words, the Coulomb's constant multiplied by the charge and then divided by the distance squared. Okay, now getting on to moving charges or our magnetic fields. So, as I said before, electrostatics concerns charges which have which exert forces on one another due to their electric fields. But now we're getting on to moving charges. So when a charge moves, it is going to generate a magnetic field. So point charges moving through an electric field have a force exerted on them according to the right-hand motor rule. And this basically just tells us that the force, the magnetic force, the direction of the field, and the velocity of the charge are all going to be perpendicular to one another. So you can just use your fingers. The strength of this force on a moving charge is going to be given by force equals QVB sine theta. Getting onto flux, strength, and production. So, magnetic substances and electromagnetics produce magnetic fields. Remember, magnetic field lines are drawn from positive to negative. So they're drawn from the north to the south. The magnetic flux is the quantity of magnetic field passing through a given area, and the magnetic field strength is the flux per unit area. So a way to think about this is if you have this square area here, and you have 4 magnetic field lines passing through it, the magnetic flux of this area might be 4, right? However, if we consider this to be, or if we wanted to find the magnetic field strength, and this was, say, 4 meters squared, then 1 meter squared per unit area is only going to have a magnetic field strength of 1 Tesla. So the magnetic flux tells us like how many lines pass through any given area at all. You know, you can have an absolutely massive area and have a lot of magnetic flux. However, with that same massive area, you could have a very small magnetic flux density, because even though it's a massive area, you know, the reason that the magnetic flux is so high is because it's a massive area, but when you actually take it per unit area, there's not actually a lot of lines passing through each unit area. And this is, of course, why the magnetic field strength is the flux per unit area. So, the magnetic flux is given by the magnetic field strength multiplied by the area, of course. And then we can determine the direction of the field given current or vice versa using the right hand rule. So this is shown down here. So if you get out your right hand, you can use this to tell you the electric current and the direction of the magnetic field around a current carrying wire and also around a solenoid. So we'll go over the current carrying wire one first. So when you're considering a current carrying wire, of course the current in the wire is like moving electrons, moving charge, which is going to generate a magnetic field. So when you're considering a current carrying wire, your thumb is going to be pointing in the direction of the conventional current, not the actual current, the conventional current. Remember, conventional current is opposite to the actual current. And a lot of questions are just going to give you the current in terms of conventional current anyway, so don't worry too much about it. It's mostly just when you get into questions involving moving charges, like singular charges rather than current carrying wires. So yeah, your thumb is going to be the current, and then your fingers are going to wrap around and they're going to tell you the direction of the magnetic field. And it's going to act kind of in this circular way. around the wire. Now, getting on to our application of the right-hand rule with solenoids. So, remember, a solenoid is a coil of wire, current carrying wire, wrapped in this kind of, with like this core in the center. And because we have this coil, every single section of this current carrying wire is going to be generating a little magnetic field around it. So this section is going to be like this, like this. It's going to be generating all these little like loops around each section, because that's what we've seen in this example over here. And this all accumulated together is going to generate this combined magnetic field through the center of the solenoid. So when we're using the right-hand rule with solenoids, we need to consider our fingers being the current instead of the magnetic field as they were with the current carrying wire. So our fingers are going to represent the current in the wire, and then our thumb is going to represent the direction of the magnetic field. So our thumb is going to be pointing towards north. So in this example here, our thumb is going to be pointing to the left, because that's the direction of north, and because of that we can tell which of these is the we can tell the direction of the current. So our fingers are going to be wrapping around this way, or like kind of away from you. So this tells us that the conventional current is going to be moving kind of in this direction, which makes absolute sense. Remember, because it's the conventional current, so conventional current moves from the positive to the negative. Of course, you might remember from year 11 when we went over electric circuits that electric current is generated by moving electrons, moving from the negative terminal to the positive terminal. However, that is the actual current. The conventional current is the opposite of that, as I said before.